Hey, Alex.
Hello.
How's it going?
Not bad. Just joining class a little early.
Cool.
How you doing, Professor? How was your weekend?
It was good. Yeah, I visited a friend over the weekend, so now that more people are getting vaccinated, we're feeling more and more comfortable doing that. So yeah, it was good. How's your weekend?
Not too bad, not too bad. Didn't do much though.
Ah, so that's good. Yeah, resting, especially during these times, is tough. All right, it's 2:30, so let's go ahead and get started today. So good afternoon, everyone. How's everyone feeling today? Tired?
Excited for summer break.
Yeah, for sure. I hear you. I hear you. So for the first 5 minutes today, we do have a special guest, and so we have someone from Titan Rover today. I'm going to tell you about the Titan Rover project and to hopefully entice you guys to join that project for next year. Right? All right. So Josephine, whenever you're ready, you can go ahead and share your screen and you can start.
All right, thank you, Dr. Tran. One moment. All right, just to confirm, it's all ready to go.
I see it.
All right, hey everyone, I'm Josephine from Titan Rover, and I'm the club president. I'm currently a junior mechanical engineering undergrad, but I'm just here today again to quickly go over what Titan Rover is all about. So here's a quick video kind of showcasing overall what our team is about.
Titan Rover is a club that aims to prepare students in STEM-related fields with technical and innovative knowledge through experiential learning. Members have the opportunity to better their skill sets through designing, manufacturing, and programming a mock Mars rover. We compete in the annual University Rover Challenge, which draws in almost 100 university teams from around the globe that undergo a rigorous selection process to be the final 36 teams invited to the field competition at the Mars Desert Research Station near Hanksville, Utah. The goal of the competition is to design a rover that could one day help Mars colonists. Teams in the rover must complete 4 tests: extreme delivery retrieval, equipment servicing, autonomous traversal, and science analysis. In the past 7 years, we've been selected to compete in 5 URC finals. We take pride and value the diversity of our multidisciplinary team members. We have sub-teams that focus on mechanical engineering, electronics, programming, life sciences, and business. But much like our rover's distinct components, those different sub-teams are essential parts that work together to make our rover ready for competition. We invite you to join us in our legacy and become part of Titan Rover. Titan Rover is a club that aims to prepare.
All right, and also here too is Van Wen. He's the project lead for the team and head of the mechanical sub-team as well. So he and I will give a quick rundown and he can describe some of the overviews of our team. So our team is composed of mechanical control, science, electrical, and business, but today we'll have a focus specifically on the mechanical sub-team. And Van, would you like to share some of the team structure?
Hi guys, I'm Van. I'm the project lead. Sorry, I came in late. But so if I know most of you guys are mechanical engineering students. So if you join for the senior design class, so it's going to be a year-round class next year for upcoming seniors. And so if you're interested in joining, it will mostly be for the mechanical team. So we are we are in charge of the mechanical and physical aspect of the rover. So we design all the systems mechanically wise, like the chassis, robotic arm, the mobility system, and the mechanical science system. And then we're also communicating with the electrical and controls team, which is the club side of the organization. So you gain a lot of exposure and gain a lot of communications and working in a team environment.
Yeah, so in addition to learning about mechanical, you can kind of expose yourself to things outside of that realm. So you can probably learn about if you're interested in inverse kinematics and how that affects our robotic arm. But further going into the mechanical team structure, as Van has mentioned.
So there's many roles in the mechanical team. For example, there's the chassis manufacturing team, there's the robotics team, there's a mobility team. So in each sub-team, you get to develop different skills. Like for example, in the chassis team, you develop your finite element analysis skills through and analyzing our chassis. You get to work with in a machine shop environment. You get to learn CAD and CAM softwares and so on. And so if you're interested in more of the vibrations, so you can join the mobility team where you use more MATLAB and more about learning more about suspension in a drivetrain and so on.
Yeah, and anything related to robotics wise, for instance, you're interested in the robotic arm of the rover. It's responsible for doing dexterous tasks like flipping switches and pressing buttons. If that's something more interested of you, if you really enjoy kinematics, then that would be the robotics lead or robotics team for your interest. But other than that, that brings our presentation to a close. But thank you all for listening, and thank you, Dr. Tran, for allowing us to present. I can input some of the information that you see on the screen into the chat box.
Yes, thank you so much, Dr. Tran, and everyone else.
Yeah. If you can put the information in the chat, I think that'd be probably easier than I think people can just copy and paste that information. But thank you guys. Yeah, it's always a pleasure to host sessions from the student projects, and Rover is one of our best student projects. So definitely if you're looking for a project to join next year, definitely Rover team is a great team. So thank you guys.
Thank you. Have a good day.
Thanks, you too.
Thank you.
Okay. And so let's resume with our regularly scheduled programming. Okay. All right. And so today, what we're going to talk about, we're going to continue along with our lecture notes on radiation exchange. Okay. Before we do that, let's talk about the midterm a little bit, because I did finish grading those last week sometime. I think it was Thursday. And so the average for the midterm was 39 out of 50. Okay, so it's about a 78%. Okay, so it's good. So convection's always, I think, probably the most challenging topic in heat transfer, and so I think you guys did really well, considering how challenging that was. So that was good. Okay, and so your scores and my feedback should be posted on Canvas already, and so please take a look at that. Especially as you're preparing for the final exam, I think the feedback that I gave you there would hopefully be helpful for that. Okay, I've also posted the solutions for the second midterm, and so you'll find them on the Canvas site under the file folder called Solutions, and then you'll see the file there for midterm 2 solutions. So you can check those out as well. Okay, that's it. Right? And so we're very quickly approaching the very end of the semester, and so we have 4 class sessions left. And so let me just kind of break it down, what my plan is for the last 4 class sessions. Okay. And so I'll label them just lectures 1, 2, 3, and 4. Okay. And so, today counts, of course, and today will be lecture 1. And so today we're going to be, my plan is to cover radiation exchange. Okay. Right. And so I'm hoping to finish up lecture notes 12, and then at least, start lecture notes 13. Okay. on Wednesday, we're going to continue along with that. And so we're going to continue along with radiation exchange. Okay. Next Monday, I think we're still going to need a bit more time with radiation exchange, but maybe not the whole time. Okay. And then after that, I have one more kind of very small topic to cover in this class about environmental radiation. Okay. And so it's going to be very, very short, but you know it's basically, you know, especially because it's a relevant topic nowadays about climate change and all that stuff. It's basically how can we apply, you know, a lot of what we're learning in this class, especially the radiation unit, on things like climate change and how that kind of works at a very basic level. And so, you know, we're going to go just very, very surface level, but you know, we're at least going to talk about it a little bit. Okay. And then for the very last class session next Wednesday, since it's our very last one, I plan to have a review for the final. Because we do have a final exam in this class, and so I want to make sure that I have one class session dedicated for that. Okay. Actually, let me look up what day the final exam is going to be. Our final exam. Our final exam is going to be May 19th. And so that's going to be on the Wednesday. It's going to be Wednesday, May 19th from 3 p.m. to 4:50 p.m. Okay. Okay. And then we'll use the same format as we have for the other exams. And so, you know, it'll be conducted through Canvas. And so you'll take the exam on there. I'll open up the Zoom sessions in case you wanted to come in and ask questions. And then, you know, and then we'll close it up from there. Okay. I do plan on it being a little bit longer than the midterm exams, but not by that much. And so I'll probably just add maybe one conceptual question and one problem solving question. Okay. But we'll talk about that a lot more next week. Yep. Mm-hmm.
A quick question for that time. Is it possible for to take it the exam early, or because like I have class from 4 to 5:15?
So that's it's going to be during finals weekend. So there's not going to be any classes during that time.
Okay.
Yeah. So the week is all free except for exams.
Okay.
Unfortunately, I think we do kind of have to stick with this time because, you know, we have to account for, you know, the fact that if some students have exams either after this or before this, and so you know, we kind of have to stick to that time, and so it's a little bit hard for me to kind of give a bit more time than what's allowed.
Okay. All right, thank you.
Yep. All right. So any other questions on the midterm average or on the final exam or just the plan for the rest of the semester?
Is the final exam only on radiation, or is it going to be throughout the whole year?
So it's going to be cumulative, and so it's going to cover stuff from, you know, from the beginning. It's not going to cover absolutely everything, you know, because that'd just be way too much to study. And so I've hand selected certain topics. And so thanks for reminding me, actually. So I did post a study guide for the final exam, and you can find that on the course website as well. And so if you go under files and you go under I think lecture notes, and it should be there. After the class, I'll send an email just to kind of show you where it is and give you a direct link for it. But it is cumulative, but I've basically, what I've done is I've basically taken each unit, which is, you know, conduction, convection, radiation, and I've selected, you know, 2 or 3 topics. Because usually, you know, in each unit we have like 5 or 6 different ones, but I've selected 2 or 3, you know, just to help make your studying a little bit more efficient. Yeah. So when you're studying for the final exam, you know, the first thing you should look at is a study guide, because that's going to tell you what you should and what you should study for and what you don't have to study for. Okay. All right. Any other questions before we get started for today? Okay. All right. All right. So I think last Wednesday where we left off is we were just about to do an example. So let me start with that. Okay. because we had just gotten done talking about, you know, this idea of radiation exchange. Whereas if you have two surfaces, if you have two surfaces, you know, and they're at a certain temperature, they're going to exchange heat with each other through radiation. Okay. And up to this point, we're kind of just building up the concepts and building up the skills that we need to actually compute this. Okay. All right. And so for this example, let's consider a situation where we have a brick wall. Okay. And let's assume that it's a very hot brick wall, like extremely hot. Okay. And so let's say that the temperature of this surface right here is going to be 500 Kelvin. Okay. So very, very hot. And then right next to the brick wall is going to be a bed of coals, which is unreasonably hot. Okay. And so let's say that the temperature of the coals here is 2000 Kelvin. Okay. So we have like coals from hell or something like that. And so another thing that we're given in this problem is the spectral emissivity of the brick wall. So it looks something like this. Okay. And so on the x-axis here, we have the wavelength. And this is in micrometers. Okay. Right. We start our graph at 1.5, and then we're going to end at 10 micrometers. Okay. And then on the y-axis here, we have the emissivity, which is epsilon. Okay. And then our graph looks like the following. It's going to be just like that. It's going to go up here. And then at 10, it's going to go up here. Okay. For each of these levels, so our emissivity is going to start out at 0.1 in between 0 and 1.5 micrometers. Okay. And then it's going to jump up to 0.5 for the emissivity. And then at the end, it's going to jump up to 0.8. Okay. And remember, you know, we have these graphs just to illustrate the fact that, you know, different objects there, the thermal properties might change, or the radiation properties might change as a function of wavelength. Okay. Because remember, radiation is made up of all these electromagnetic waves that you see throughout the, or you, I guess you don't see. And, you know, and the behavior of these things change as a function of the wavelength. Okay. All right. And so this example here has three different parts. Okay. And so for the first part we're going to compute is the total emissivity of the brick wall. Okay. And so we're going to work on this graph right here and then use it to compute a total. Okay. Next, we're going to compute the total emissive power of the brick wall. Okay. Well, in other words, how much radiation energy is this brick wall giving off? Okay. Right. And so parts 1 and 2 can be done independently of the coals. And so parts 1 and 2 don't involve the coals at all. Okay. But in part 3, we're going to bring the coals in there. Okay. And so in part 3, we're going to compute the absorptivity of the brick wall from the coals. Okay. Because the coals are going to radiate some heat onto the wall, and then that heat is going to be absorbed by the wall. Okay. And then we're going to compute basically that absorptivity. Okay. All right. And so to do this, you know, the key is going to be this graph right here. Okay. Right. The key is going to be this graph and how we use this graph along with our integrals from the last set of lectures. Okay. All right. So any questions on this so far? Okay. All right, and so what we're going to do is we're going to take this graph right here and integrate it from 0 to infinity for the wavelength, okay? Right, and so first thing we're going to compute is the total emissivity. Okay. And remember that that formula is given by the following, and so we have E total is equal to integral from 0 to infinity of epsilon of lambda, right? And so that's the emissivity as a function of lambda, which is what we have on the previous page. Okay. Okay. Next, we have the emissive power of the blackbody, okay? And this is a function of lambda as well as the surface temperature. Okay. Okay. And then we're going to divide this by the temperature, the total emissive power of the blackbody, which is just a function of the surface temperature. Okay. All right. And so the key to this part here, where most of this we're going to evaluate using our tables, but in this case, because our epsilon of lambda here is a discontinuous function, which is what we see here. Okay. What we need to do is we need to break up this integral into 3 different zones. Okay. Okay. And for this problem, I use 3 because we have 3 different steps here, right? So we have the bottom step, we have the middle step, and we have the top step. Okay. And so we need to integrate over those 3. Okay. All right. And then our breaking points for our integration bounds are going to be whenever the function steps up. Okay. All right. And so now our formula for the total emissivity is going to be epsilon 1 for the first zone, and the first zone goes between 0 and 1.5 micrometers. Okay. Okay. Next, we have the second zone, and so the second zone has an emissivity of epsilon 2. Okay. And then this is going to be the integral over the second part of the zone, which is integral from 1.5 up to 10. Okay. And finally, we have our third zone, which starts at a wavelength of 10 and goes all the way up into infinity. Okay. And so we have epsilon 3. Okay. Of integral from 10 to infinity of EBB lambda TS d lambda divided by EBB. Okay. Right. Where in this formula here, epsilon 1, epsilon 2, epsilon 3 are the 3 different levels, right? And so for here we have 0.1. Okay. Because that's the first zone. And so you can see for the first zone, from 0 to 1.5, we have an epsilon 1 of 0.1 here. Okay. And the second zone, this is 0.5. And the third zone here, we have 0.8. Okay. All right. And so those are all the integrals for our different zones. And so what we have to do now is we have to perform these integrations here. Okay. And we're going to use the table for that. Okay. And so we're going to compute, the product of lambda and TS for, each of our 2 points. which we have 2 here. So we have 1.5 and 10, okay? And then compute our f values from that. And then from the f values, we can evaluate these integrals, okay? All right, so any questions on this? Okay. All right. And so another way we can write this integral, so we can say that epsilon tot is equal to epsilon 1 times f from 0 to 1.5, okay, plus epsilon 2 times the product f from 0 to 10 minus f 0 to 1.5, okay, plus epsilon 3. Since the upper bound for for the third integral is infinity, that instead of an f value, we're just going to plug in 1, okay, minus f from 0 to 10. Okay. All right. And so the way that we and so remember the way that we compute the f values is we use the table. Okay. And in fact, it's table 12.2. Okay. And so using 12.2, we first compute the product of the wavelength times the surface temperature. Okay. And so first we're going to do lambda 1 times Ts, where Ts is the surface temperature of the brick wall. So this is 1.5 micrometers times Ts, which is 500 K. Okay. And this is equal to 750. Okay. Micrometers K. Right. And so if we look up in the table, what we get is F from 0 to 1.5 is equal to just 0. Okay. Right. We can do the same thing for the second integration point, just lambda 2 Ts. Okay. And so lambda 2 is 10 micrometers. And so we perform the multiplication, we end up with 5,000 micrometers K. Okay. And so this tells us that F from 0 to 10 is equal to 0.634. Okay. Right. And so now that we have these values, we just have to plug them in up here. Okay. And so this F 0 to 1.5 is going to go right here. It's going to go right here. Okay. F from 0 to 10 is going to go right here. Let's go right here. Okay. And we plug in all those things as well as epsilon 1, epsilon 2, epsilon 3. And then what we get is epsilon tot is equal to 0.61. Okay. All right. And so that's an example. And so this is not too different from, I think, the example we did at the end of the last lecture notes, where we had this graph where the emissivity varies as a function of wavelength, and then we use the table along with these. We use the integrals along with the table in order to compute kind of the total emissivity. Okay. All right. So any questions on this? Okay. Right, and so now that we have the total emissivity, what we can do is we can use this to compute the total emissive power. Okay. And so the total emissive power is just going to be, remember we give that the symbol E, okay? And so this is going to be epsilon total, which is what we just computed, times the emissive power of a black body, Okay. And so the emissive power of a black body, we know that from when we first started radiation. And so it's going to be sigma times the surface temperature to the fourth power, right? Where remember, we have to compute, temperature in terms of Kelvin, which we already have here, okay? And so we just plug in all the numbers for that. And then what we get is 2,162 watts per meter squared. Okay. And so that's the total amount of radiation energy that this brick wall is giving off, okay? And so because its emissivity is 0.61, right? What that tells you is that it's only giving off 61% of kind of the possible amount of radiation energy at this temperature. Okay, and that 0.61 reflects the fact that a brick wall is not a perfect surface, right? And so it's not going to give off radiation energy as efficiently as a black body. Okay, and so in this case, it's only 61% efficient, which is still pretty good for a brick wall, actually, all things considered. Okay, so any questions on this so far? Okay. All right. And so the last thing that we have to do in this example is to compute the total absorptivity from the coals okay. Right. And we're going to make one key assumption here, and that assumption is going to be that the surface is diffuse. Okay. Okay. And remember, what that means is that the absorptivity of the surface follows the same trends or has the same wavelength pattern as the emissivity. Okay. Right. And so because it has the same spectrum or the same spectrum as the emissivity, we can compute the total absorptivity in exactly the same way. Okay, so total absorptivity is going to be alpha tote, okay, is equal to epsilon 1 f 0 2 1.5 plus epsilon 2 f from 0 to 10 minus f 0 2 1.5 plus epsilon 3 1 minus f 0 to 10. Okay. Right, and so we have the same integrals. I'm kind of skipping over the integrals in this case because it's it's kind of a lot of writing, but we can use the same f values, or we can use the same epsilon values. Okay. The difference here is that because we're getting the absorptivity from the coals, okay, when we compute the f values, when we compute the f values, we have to use the temperature of the coals because this is the absorptivity from those coals. Okay. Okay, because if you look at how we did part one of this problem. In part one of the problem, when we computed lambda 1 TS, we used the temperature of the brick wall, okay, which was 500 Kelvin. But when we do this from the coals, we have to use the coal temperature, which is 2000 Kelvin, okay? And so as an example, we're going to compute lambda 1 TC, okay? And so this is 1.5 micrometers times 2000 Kelvin. Okay. And so we multiply this together, we get 3000 micrometers Kelvin. Okay. And so if we look that up in the table, what we get is F from 0 to 1.5 is equal to 0.273. Okay. And so our F values here are going to be a bit different because of the because we're working at a different temperature because we're working from the coals. Okay. All right. So any questions on this before I finish up this example here? Okay. All right, and so let's do the same thing. And so we'll do lambda 2 TC. Okay. And so we multiply 10 micrometers times 2000 Kelvin. We get 20,000 micrometers Kelvin. Okay. And so we get F from 0 to 10 is equal to 0.986. Okay. And now that we have the F values, we just plug in the same spectral emissivity. What we get is lambda tote is equal to, or alpha tote is equal to 0.395. Okay. All right. And so what this tells us is that our brick wall is only absorbing 39.5% of the radiation that the coals are giving off. Okay. All right. And one more note, just for kind of conceptual definition reasons. Okay. And so we assume that the surface was diffuse, right? And that's to say that the spectrum for the emissivity and the absorptivity is the same. Okay. But since epsilon tote does not equal alpha tote, okay, these two are different. Okay. And because of that, what we say is that the surface is not gray. Okay. Because in order for the surface to be gray, the total emissivity and the total absorptivity, those have to be exactly the same. Okay. All right. So any questions on that? Okay, so this problem, the reason I did this example was, part of it was to kind of illustrate the difference between diffuse and gray, but another was to kind of give you some more looks at how to use that table for integration. Okay, because that's kind of a big part of this unit. Okay, all right, and so the other big part of this unit, which is what we're going to spend, all the rest of our time working on over the next week, is to talk about, how do we actually compute radiation exchange between surfaces. Okay. Or in other words, if we have a situation where we have, one surface here, and it's just like some patch, okay, and maybe we have another surface here. How do we actually compute, how much radiation goes to, from here to here, and how much radiation goes back to there? Okay, because we know that as long as an object is at it has some temperature, it's not at absolute zero, then it's going to give off some radiation, and then that radiation has to be absorbed or taken in by some other surfaces. Okay? And if every single surface is doing that, then then it would be nice to have a way to kind of to quantify how much these different surfaces exchange radiation with each other. And so in reality, this is a very complicated process that we'll only be able to compute things for the very simplest things. But in general, we can say that the radiation exchange between surfaces depends on these three factors. Okay. And so the first factor is the geometry or orientation of the surfaces. Okay. Okay. Next is going to be the radiative properties. And so these are things like emissivity and absorptivity. Okay. Okay. And the last one that's going to depend on, of course, is just the surface temperature, right? And so, hotter objects will radiate more heat. And so that's pretty straightforward. Okay. All right. And so far, what we've done in radiation, we're able to look at the surface temperature, just because, we've always been able to do that. Okay. So that part's good. And so, we know how to do that. We just spent a good amount of time talking about radiative properties, things like emissivity and absorptivity. Okay. And so for the time being, we're going to say that we're good on that. Okay. What we don't really have a good handle on yet is how to quantify this. Okay. Because, depending on the geometry of your surface and how it's oriented compared to the other ones, this is going to have a really big impact on how much radiation is exchanged between surfaces. But it's also the most complicated one by far. And so, because geometry is a very, very complicated, can be a very complicated thing, especially if you're designing, very complicated looking engineering devices. Okay. And so to come up with a way to quantify those things in a useful way in order to perform radiation calculations is really tricky. And, and this is another thing that we're going to have to rely on tables for. And, for just kind of for this class, we're going to have to rely on pretty simple geometries. But, at least, we'll be able to kind of scratch the surface and kind of just introduce kind of the general concepts on how we actually do this. Okay. All right. And so one thing that's going to help us out, with these calculations quite a bit is this thing known as a view factor. Okay. And so what the view factor is, it's basically, it's defined as the fraction of radiation leaving one surface that is intercepted by another surface. Right, and so I'm gonna use IJ notation here, and so I'm gonna call one of the surfaces surface I, okay, and so that's gonna be the surface where the radiation is leaving, from, okay, and so we're gonna say the view factor is the fraction of radiation that leaves surface I, okay, that is intercepted by surface J. Okay. All right, and so we're going to define what that, the formula for the view factor on the next page, okay, as well as, to state some rules for it, okay. All right, so any questions on this? Okay. All right, so the view factor, we usually give it the symbol big F. Okay. I know it's a bit confusing with the integration F's that we talked about before, but this is different, okay? And we always give it two subscripts, okay? I and J, which have the same meaning as before, okay? And so I and J are just two different surfaces, okay? I being the surface where the radiation is leaving from, and J is a surface where, you know, the radiation is being intercepted at. Okay, and so this is going to be equal to Qij divided by AIEI. Right. And so let's define all of these characters here. Okay. All right, so let's define Fij first. Okay. And so this is the view factor from it's going to be the view factor from surface I to surface J. Okay. This Qij here is this is the actual amount of heat transfer that's that's going from I to J. Okay. And then on the denominator here, we have AIEI. Okay. This is the kind of the total amount of radiation emission that surface I is putting out. Okay. Okay. And so here you can see why you know this this view factor here is often described as a fraction, right? And so in the denominator here, that's kind of the total amount of radiation that the surface is producing, right? And so the fraction of that actually hits surface J, or the amount that hits surface J, which is Qij, if you take the ratio in between these guys, you know, it's always going to be something between 0 and 1. Okay. And so that's another thing to remember with these view factors is that they, you know, it's a fraction, and so it goes between 0 and 1. Okay. All right. So any questions on the definition of view factors? Okay. All right. And so I'm not going to go through the derivation of this of this equation here, but you know I kind of just want to explain it kind of intuitively. And so you know the way that we actually use this in practice is a few different ways. Okay. And so I want to focus more on, you know, how we actually use this in practice, some interesting rules that these view factors follow, and then do an example with it just to kind of illustrate that whole thing to you. Okay. All right. And so often, you know, often what you're going to do, the way that you approach these problems is that you're going to come across a certain geometry. Okay. And so based on a problem geometry, what you can do is you can, there's basically big tables for these that show a bunch of these view factors, okay? Right, and so the first thing you should look at is a table. And the table in the book that that I've used, you know, for all the problems in this class is table 13.1. Okay. Or the other way that you can find the view factors is through inspection. Okay, and I'll kind of show you what I mean by that. And because sometimes it's a little bit obvious, you know, what the view factor should be in certain situations. Okay. Right. And so using this, you know, you'll be able to compute either one or multiple view factors in a given problem. Okay. Okay. And so that's you know, that's probably the first thing that you should do whenever you come across these radiation problems, is to see, you know, what view factors can I compute based on the table or based on inspection. Okay. All right. And so the next thing that you should do, because usually, you know, in all these problems, you're going to have multiple surfaces, at least two. Okay. And so you're going to need to do find all the other view factors in the problem. And the way you're going to find the other view factors is to use these view factor rules. Okay. All right. Right. And so the rules are going to help you compute all the other view factors. But, you know, probably the first thought that's going through your mind is, you know, what do I mean by all other view factors, right? And so, you know, how many view factors are there in a problem, and shouldn't there only be one? And so that's, you know, I remember when I first learned this, those were kind of the thoughts that were going through my head. So let me kind of illustrate this, okay? And so let's say that we kind of have a simple situation. We have one surface and another one, okay? And so we'll call this surface 1, and we'll call this surface 2, okay? Right. And so let's say that we compute the view factor one way, okay? And so if we want to compute the view factor from surface to 1 to 2, we call that F12, right? Okay. But, you know, we know that surface 2 is a perfectly legitimate surface as well, okay? And so surface 2 is going to be radiating heat, and some of that is going to be intercepted by surface 1. Okay. And so the view factor from surface 2 to surface 1, we call that F21. Okay. And so that's, you know, and so that makes a lot of sense, right? So whenever you have one surface radiating to the other one, the other surface is going to radiate back to it, you know, and then these view factors are going to be different, and so they're not going to be the same most of the time. Let me give you one other situation here where which might be interesting. Okay. And so let me kind of introduce this by asking the question: is it possible for a surface to radiate itself, right? And so is it possible for surface 1 to radiate, and if that just to come right back to that surface, right? And so if we wanted to find that view factor, we can do that by define that to be F11. Okay, and so F11 here would be the amount of radiation that surface 1 gives off that just gets absorbed right back into it. Okay, and then we can do the same thing for surface 2, right? So any radiation that surface 2 will emit that just comes right back to it and gets reabsorbed, we'll call that F22. Okay. And so is this even possible for this to happen? And the answer is yes, actually, believe it or not. Right? And so it might be hard to imagine with the ones I have here because you know, these are kind of some bad examples. But on the next page, let me show you an example of how that's possible for a surface to kind of radiate itself. Okay. Okay. So any questions on this so far? Okay. All right, and so let's say that we have a concave surface. Okay. And so in other words, let's say we have a surface that looks like this. Right. Right, and so if we have a concave surface, every part of the surface is going to be giving off radiation, right? And so it's going to be giving out radiation kind of like this, okay? Right. What you can imagine is that, because the surface is concave, the radiation that comes off this surface and travels in this direction, it's just going to hit the surface again because the surface is just naturally concave like that, okay? Right. And so if you have a concave surface where you have some, parts of your surface that kind of, that can kind of, where radiation comes off and can hit each other, okay, or hit back on itself, then what we have is a self view factor that's going to be greater than 0 here, okay? Okay. And so anytime you have some kind of concavity or a surface that can kind of wrap around like that, then you're going to have a self view factor that's not going to be 0. Okay. But for cases where the self view factor is 0, are going to be surfaces that are generally flat or convex. And so in these cases, the self view factor is 0. And then, what we say is that there's no way for the surface to radiate itself. Okay. And so this is a big part where, looking at the geometry and seeing, what simplifications you can make is going to play a big impact. Okay. All right. Any questions on concave and convex surfaces here? Okay. All right. And so let's go over the 2 rules that'll help you compute the view factors for everything else. Okay. All right. And so the first rule is known as the reciprocity relation. Right. And so this basically tells you a way, if you have Fij, then you can use that to compute Fji. Okay. Right. And so let's say that you have Fij, and so let's say that this is something you either looked up from a table or you found it through inspection, right? Is you found this somehow, okay? And what the reciprocity relation is, it's going to allow you to compute Fji, okay? Right. And so, they're not just equal to each other. And so what you have to do is you have to multiply this. You have to multiply the left-hand side by Ai, okay? And to multiply the right-hand side by Aj. Okay. Oops. Right. And so if you have the view factor in one direction, say Fij, if you multiply that by the area Ai, then you can compute the view factor in the other direction, the reciprocal direction, Fji, but you have to multiply that by Aj. Okay. And so using the surface areas of the objects, you can use that to get the reciprocal view factors, whatever that is. Okay. Right. All right, and so that's the first rule. Okay. The second rule that we'll go over here is the summation rule. Okay. And so the summation rule only pertains or only applies to view factors for enclosures. Okay. Because the unique thing about enclosures is that, you know, every bit of radiation that comes out has to be absorbed by something eventually. Okay. Right. And so if you have some kind of enclosed space, right? Okay. Right. And so let's say that, you know, each of these surfaces here are radiating out. Okay. Okay. Because it's enclosed and no radiation can come out, you know, then what we have to say is that, you know, none of this radiation can escape. So everything has to be absorbed eventually. Okay. And so for these situations, you can take advantage of that to form one more relationship with the view factors. Okay. All right. So any questions on this? Okay. And so for enclosures like this, we have the following rule. Okay. Right. And so once again, we're going to start with the view factor Fij. Okay. Right. And then if we sum up all the view factors over J, okay, where N here is the number of surfaces in the enclosure, okay, this all has to equal to 1. And so if you add up all the view factors for surface I in an enclosure, then they all have to sum up to 1 because all of that radiation has to be absorbed eventually. Okay. All right. And so let's use these rules, and then let's do an example to see you know, how to actually compute these you know, these view factors. Okay. All right. And so let's do an example here where let's say that we have a sphere, a tiny sphere and a bigger sphere, okay? All right, and so we have a sphere enclosed in a sphere, okay? The inner sphere, we'll call that surface 1, and the outer sphere, we'll call that surface 2, okay? Right. And let's just say, you know, maybe magneto's here or something like that, but sphere 1 is just kind of floating inside sphere 2, okay? And so for somehow it's being held up and there's no, and it's just empty space between them, okay? All right. And so in this problem, we want to compute the all the view factors, okay? And then here we have 4 view factors. And so we have the 2 self view factors. Okay, so we have F11, F22. Okay. And we also have F12, which is the view factor from going from surface 1 to surface 2, or the inner sphere to the outer sphere. And then we have F21, which is the you know, the view factor going from the outer sphere to the inner sphere. All right, so any questions on this setup before we start with the problem? Okay. And actually, let me maybe make one more part of the drawing here to make things a little bit more clear. We'll say that the inner sphere here is solid, okay? And so there's nothing on the inside. And so the only thing we're concerned about is the radiation in the cavity in between, okay? All right, and so let's go through each of these view factors here, and let's see if we can compute them. Some based on inspection, and then the others based on the rules. Okay. All right, so let's start with F11. Okay. And so F11 is the self view factor for the inner sphere. Okay. Right, and so one thing that we observe for the inner sphere is that it's a convex surface, right? And so it's kind of rounded like this, and the radiation is coming off from the outside. Okay, and so since it's convex, what we say is that it's impossible for it to radiate itself without hitting another surface. Okay. And so since surface 1 here is convex, what we can say is that the self view factor, F11, is 0. Okay. All right. And so that's an example of a view factor that we can obtain just purely from inspection. Okay. All right. And so now that we have F11, we can use this to compute F12. Okay. Because since we have an enclosure here, since we have a totally enclosed system, we can use the summation rule to compute F12. Okay. Because by the summation rule, what we have is F11 plus F12, okay, which is the summation of all the view factors coming from surface 1, okay. All of this has to equal to 1, right? And so since we just computed F11 here, so we know this one's 0, what this tells us is that F12 has to equal 1, okay? Right? In other words, what this says is that all the radiation that leaves surface 1 has to hit surface 2, okay? Okay. Which, intuitively, if you look at the figure, kind of makes sense, right? And so if you look at the figure here, any radiation that comes off the inner sphere, there's only one place for it to go, which is the outer sphere. Okay. Right. And so next we have F21. And so we can, now that we have F12, we can use the reciprocity relation to compute this. Because what we know is F12 A1 is equal to F21 A2, okay? And so we solve for this, we say F21 is equal to A1 divided by A2, okay, times F12. Okay. And so in this problem, I didn't give you the radii, but normally you would know the radii of these spheres, okay? And if you know the radii, then you can compute this very easily. Okay, so you just take the ratio of their surface areas. Okay. All right. So any questions on this so far? Okay. All right. And so that's F21. And so the last one we need to do is F22. Which is the self view factor for the outer sphere, okay? Okay. And so for this, we can just do the summation rule, okay? Because we know that F21 plus F22, okay? This has to sum up to 1, okay? F21, we just solved for this in the previous step. Okay, and so what this tells us is that F22 is equal to 1 minus F21. Which is going to be non-zero in this case because because it's a concave surface, right? And so there's going to be some radiation that comes off from the outer sphere that's not going to touch the inner sphere. It's just going to go straight to itself. Okay. All right. So any other questions or any questions on this example here? Okay. All right. And so that was a relatively simple example where, you know, we found our first view factor just by inspection. Okay. But for more realistic situations and the ones that fall into a table, you can use you know, a table to compute some of these view factors. Okay. And so the two tables, I think I only put 13.1 earlier, but 13.2 is also a table that can show you how the view factors are. Okay. All right. And so let's do kind of a little bit more complicated example, which uses the tables. And let's actually do an example where we actually compute the Blackbody radiation exchange. Okay. Okay. All right. And so the Blackbody radiation exchange is nothing more than just, you know, the exchange of heat in between two surfaces. You know, and we're going to assume that they're black bodies for now. It's going to be the exchange of two surfaces via radiation. Okay. And the way that we're going to define it is like this. Okay. And so we'll call that QEX or Q exchange. Okay. It's just going to be the difference between QIJ minus QJI. Okay. And so the difference between heat transfer from surface I to surface J minus the heat transfer from surface J to surface I. Okay. All right. And so if we put this in terms of the view factors, it looks like the following. And so this is going to look like, first let's do Qij, okay? And so Qij is going to be Fij times Ai times sigma Ti to the fourth power. Okay. And Qji is just going to be Fji times Aj sigma Tj to the fourth. Okay. Right. And so our radiation exchange is just going to be the difference in between those two things. Okay. But we can actually simplify this a little bit more because what we have is our reciprocity relationship. Okay. And so if we kind of take note of the fact that we have this quantity here as well as this quantity here, okay, these two things are actually equal to each other based on the reciprocity relationship. Okay. And so if we kind of plug that in, we can simplify this a little bit. Okay. Okay. So any questions on this so far? Okay. All right. And so if we plug in our reciprocity relation, right, which says that Fij times Ai is equal to Fji Aj. Okay. Plugging that in, what we get is Q exchange. We have two different expressions for this, and so we can put it in terms of Fij. Okay. Okay. And so one expression is going to be Fij Ai times sigma Ti to the fourth minus Tj to the fourth. Okay. And so that's one form. And so the other form of this is going to be Fji Aj, okay, times sigma Ti to the fourth minus Tj to the fourth. Okay. And so either one of those is fine, okay? And in fact, sometimes it's more convenient to compute one view factor over another one, okay? Sometimes it's more convenient to compute Fij versus Fji, okay? And so depending on which one is more convenient, you can use that expression for the radiation exchange, okay? All right, and so we're almost out of time, but I do want to just kind of introduce the next example here, and then we'll pick that up on Wednesday. But before I do that, are there any questions on this so far? Okay, all right, so let me just introduce kind of the geometry for the next example, and then we'll pick this up on Wednesday. All right, and so in this example, let's say that we have a rectangular furnace. Okay, and so let's say that the rectangular furnace has 3 walls. Okay, and so we'll call this surface 1, we'll call this surface 2, and we'll call this surface 3, okay? And we'll say that each of them are at different temperatures, and so this one is at 1000 Kelvin. Down here we have 800 Kelvin, and then over here we have 600 Kelvin, okay? And this, let's say that this length here is 0.5 meter, so 0.5 meters. And this length down here is 0.1 meters, okay? Right. And then on this last surface here up top, let's say that we just have room temperature conditions. Okay, and so T infinity up here we'll say is just 300 Kelvin. Right. And so a little bit more complicated of a situation than our last example. But what we'll do on Wednesday is we'll see that, and we'll use the tables here. We'll use the tables to compute the view factors, okay? And then from the view factors, we'll be able to compute the radiation exchange between each of these different surfaces, okay? All right, so thank you. So that's all we got. That's all I had planned for today. So thank you guys for tuning in, and I'll see you on Wednesday. Oh, one more thing before you guys go. So I did post the last homework assignment, and so homework 7 is up. But we'll talk about that on Wednesday too. Right. All right. Thank you guys.
Thank you, Professor.
Thanks, Nicholas.
Professor, do you have like office hours like right after this?
I don't, but I do have some time to chat. So if you want to chat, we can chat.